Hey everyone, I will be presenting our research on hierarchical summaries of multidimensional data. This is joint work with Alexandra Kim and Devesh Srivastava. Alexandra just recently graduated from UBC and Devesh is from AT&T Research. To set the context, let's begin with the observation that for many data-driven decision-making applications, we subject the data to various ML pipelines or other statistical methods. And often effective use of this exercise requires that we have a good understanding of the data set, which calls for repeated exploration and summarization of the data. And summarization is the main goal that we're after in this talk, in this work. Often these data sets tend to be multidimensional, therefore it makes natural sense to exploit the dimension hierarchies that come with the data. Turns out that a variety of different kinds of summaries are possible over multidimensional data sets, depending on whether you are looking for lossy summaries or lossless summaries, the extent of loss tolerated, the structure of summaries, and so forth. So there are various quote unquote dimensions along which to play this game. To set the context, I would like to quickly highlight a couple of key pieces of related work. Agrawal and company in KDD several years ago, they were among the first to develop both lossy and lossless summaries for hierarchical data sets. However, they were confined to a single dimension. Their algorithm has the advantage that it gracefully degrades, if you will, from the lossless case to the lossy case, and it's efficiently computable. Karloff and company in Stacks several years ago, in some ways, it can be viewed as an extension of the Agrawal et al. Approach to hierarchically constrained rectangles viewed as summaries. Unfortunately, that approach is NP-hard, even in 2 dimensions. And the reason for this is because they permit these summary rectangles, the regions permitted in the summaries, to overlap in arbitrary ways. So therefore, it's NP-hard even for 2 dimensions. However, they propose randomized 2 approximation algorithm. Another restriction of their work is that they confine themselves to lossless summaries. There is no natural extension that comes with error guarantees for the lossy case for a given loss parameter. From a different angle, Rule et al. From Sigmod a couple of years ago, they looked at this problem and proposed an algorithm called cascading analysts. The way it works is that given a size for the summary, you can think of that as a size budget for the summary that you're looking for, it finds the best possible summary under some criteria. They propose an optimal solution for 2D, which is efficiently computable. However, for more than 2 dimensions, they propose only an approximation algorithm, and the algorithm does not come with a worst case error guarantee. And this is important because in all cases, even in a case where the size budget is infinite, their algorithm always returns an approximate summary, a summary which is lossy. There's a bunch of other related work, which all I will do is flash it before you just for the sake of completeness. I won't get into the details here. So given all of this prior work, what are we after? We are interested in an approach that guarantees concise summaries, is efficiently computable regardless of the number of dimensions, and gracefully extends itself from the lossless case to the lossy case for any amount of loss that you are willing to tolerate. And finally, comes with nice accuracy guarantees, worst case error guarantees. So this is our goal. What kind of summaries? In other words, what shape of summaries are we looking for? To understand this, we need to look at the underlying lattice structure, which is what you get when you take the hierarchies that come with the dimensions of the data set and take their cross product. So there is a natural lattice space that gives you a search space from which to build summaries. Okay, as a toy example, let's consider this outdoor equipment store with these 2 hierarchies on product dimension and stored location dimension. So taking their cross product gives rise to a lattice, which I have rendered rather than as a conventional lattice diagram, I have rendered that as a two-dimensional grid. The values that you find in each grid cell, which correspond, by the way, to the leaves of the lattice, these values correspond to the ratio of the sales between two successive months. So basically, I just picked this example to show that you can do the summary either for the raw values in a data warehouse or for changes computed, in this case, for example, by taking ratio between two comparable snapshots of the data warehouse. All right, so as a preview, here is an example of a tree summary, and let me quickly socialize the summary before we get into the details of how we get one. For example, the entire region corresponding to all products and all stores, that corresponds to the light blue region, the entire rectangle covering all the grid cells. So that has a value 1 associated with it. That's like saying, for the most part, there was no change between the previous month and the current month. The ratio is 1. Let's look at some of the child regions. So this yellow region here, it has a ratio value of 1.2. So it says that for the region corresponding to all stores and insect repellents, for these 3 cells, the applicable ratio value is 1.2. So that 1.2 overrides its parent region's value. And finally, the yellow region's child, the orange single cell region over here, it has a value 0.8 associated with it, and that overrides its parent region's value. Okay, so it's basically inherently leveraging the natural tree structure that's embedded in a lattice structure. That's what we are trying to exploit in order to summarize the data efficiently and hopefully in an intuitive way. So it turns out that we have to do a little bit more work. We can't just take the raw lattice. We need to extend the lattice a little bit. Let me tell you briefly about it. So what we do here is keep track of the drill down dimensions. So let's say that this is the root of the lattice, all products, all stores. We keep track of the drill down dimensions, product dimension and store location dimension. And of course, expand them on each of these dimensions. And if you keep doing this, you will eventually get the entire lattice extended with these dimension nodes, which group together all the nodes that are obtained by starting from a parent node and drilling down along a particular dimension, in this case, product. Okay, so obviously what I show here is only a partial view of the entire extended lattice. What's the space of summaries from which to build the optimal summary, from which we seek the most concise summary? So in order to define it or understand it precisely, we start with the root of the lattice, which we've already seen, mark the root of the lattice, and alternately mark the following kinds of nodes. If you're at a lattice node, for example, root is a lattice node, and you alternately mark the following 2 kinds of nodes. Mark any one dimension child of the lattice node that you're at, and then having marked a lattice node, mark all its lattice children as you go down from the parent to the child. So alternately mark lattice nodes and one of its dimension children and all lattice children of a given dimension node. If you keep doing this, eventually we will exhaust the lattice. You will cover the entire lattice. But what you will have described in the process is an embedded, fully embedded tree, full embedded tree. So technically we are not done. What we need to do eventually is to get rid of the dimension nodes because we don't need the dimension nodes once we get the full embedded tree. All right, let's see what it looks like in our toy example. So I'm going to begin by marking the root node of the lattice. Let's say we pick dimension product. Then of course we need to mark all its lattice children. Once again, pick any one dimension child of camping equipment in all stores. I'm not doing anything below the other sibling of this node because I'm only showing you a partial view of the full embedded tree. Okay, so keep doing this and eventually you will have covered all the leaves of the lattice. So that defines a full embedded tree. Now, having done this, I told you that we need to get rid of these dimension nodes. And the way to do this is to do an edge contraction, basically merge these 2 nodes and make children of this dimension node, children of this parent lattice node. because that gives rise to the structure, okay, from the previous structure. Once again, I will keep reminding you that this is only a partial view of the full embedded tree for obvious space reasons. Now we're almost done. We are almost ready to define what a tree summary looks like. So consider a full embedded tree like the one that we saw before in the running example. Now assume that a subset of nodes have been assigned weights. Intuitively, these weights will have to come from the values that we find in the cells of the data warehouse, or intuitive, or equivalently, they have to come from the leaves of the lattice. Okay. Now, let's assume that we have a full embedded tree where magically we have come up with some weight assignment to a subset of nodes, but the root is always weighted. Suppose I have something like this, then I can do the following. Get rid of all the nodes without any assigned weights. And whenever I have two nodes, X and Y, which are both weighted, and they're related as an ancestor-descendant relationship, X being the closest ancestor of Y, directly connect X and Y with a parent-child edge. So the resulting tree is a summary embedded tree. So summary embedded tree is basically a concise representation of a full embedded tree. And that's all you need to store in practice to store tree summaries. So here's a quick illustration of what SETs, or summary embedded trees, will look like. So let's imagine that the nodes that I have highlighted in black here, the ones which have a weight next to them, those are the weighted nodes. So what is the resulting SET? This is still not an SET. I have just highlighted those nodes with weights. By the way, over here on the right, you can see the corresponding sort of 2D illustration of the summary that this encodes. And finally, this formally is the actual summary embedded tree. This is the real SET that you need to store in practice. Okay, so we have seen an example. We are ready to formally define a tree summary. Formally speaking, a tree summary comes with three components: a full embedded tree, a weight assignment, which is partial to the nodes of T, and we need to have a weight necessarily assigned to the root of T. Okay, that's always required. And finally, T sigma is the set, SET, or summary embedded tree, that we obtain from T by looking at the tree that is induced by the weighted nodes assigned weight by this weight assignment scheme. All right, that's what a SET looks like. Now, obviously, for this to work for us, there is an important property that we wanted to satisfy, which is that the value of every cell in the multidimensional data set, or equivalently every leaf value, should exactly match the value of its closest weighted ancestor in the summary embedded tree. Okay, so that's where the fact that it summarizes and the fact that there is some compression going on, that's where it comes from. What about lossy summaries? The way I define match makes it sound like it's only good for exact summaries or lossless summaries. No problem. If you want a lossy summary, let's say alpha is the loss parameter, then we can generate an alpha approximate tree summary by doing something as simple as changing the notion of match from an exact match to one that says the value or the weight of the closest weighted ancestor of the cell in question has to lie in this interval. So let's say this is the true value of the cell in question. So the weight of the closest ancestor in the summary embedded tree for that cell should lie between 1 minus alpha times true value and 1 plus alpha times true value. Okay, so that simple change defines for us a lossy summary. So as a preview, this is the lossless summary for our running example, and it turns out that this is the optimal summary. I haven't yet told you how to get it, but this is the optimal lossless summary. Now, allowing a 5% loss shrinks the size of the summary from what it was before to a fewer number of colored regions, or fewer number of weighted nodes in the summary tree. Okay. Finally, then here's the problem statement, formally speaking. Given a multidimensional data set where the dimensions come with dimension hierarchies, and that in turn induces a lattice structure, and most importantly, the loss parameter, if you have one, given all of this, we want to find an alpha approximate tree summary, tree's structured summary, which is alpha approximate, whose size is the least possible. Okay, so this is the notion of optimality, size optimality for a given worst case error guarantee. Now, before I tell you about the algorithm, let me quickly tell you about the key property that makes the algorithm possible in the first place, an efficient algorithm for finding the optimal summary. So let me say this simply because time is limited. Let T be a fully embedded tree of the lattice, T prime be any subtree of T. Let's say that I have magically obtained an optimal weight assignment scheme for this subtree. Okay? And I have an arbitrary assignment for the full tree. What the blocking property says is that I can take W and change the weights that W assigns to the nodes of T prime such that they agree with W star. And everywhere else, W remains unchanged. Okay, I will illustrate this in picture in just a bit, but let me tell you that this operation, according to the blocking lemma, this operation is guaranteed to not increase the size, or what we refer to formally as cost, of the summary. Okay, now I would like to note that it is this blocking property which makes it possible to have an efficient algorithm for finding the optimal summary from intuitively simple greedy label propagation. Okay, we'll look into the details shortly. Now, the running time of the algorithm is order of DHN. D is the number of dimensions. H is the number of levels of the lattice, which obviously is the sum of levels of the hierarchies of various dimensions. N is the number of leaves of the lattice, or equivalently number of cells in the multidimensional data set. In the Lossy case, there is a log n blow up to the running complexity. So blocking lemma in pictures. So let's say here is a subtree of some FET, full embedded tree. So T prime is a subtree of that, for which somehow we have figured out an optimal weight assignment scheme, which is equivalently a tree summary of optimal size for T prime. Okay, so this is what we have so far. Along comes an arbitrary weight assignment for the containing FET. So FET, T contains T prime as a subtree, you can see this. Now, if this is given, this transformation illustrates the possibility of taking W, the original weight assignment scheme, and changing the weight assignment scheme just on the nodes of T prime such that there alone it agrees with W star and remains unchanged everywhere else. So the point is blocking lemma guarantees that this does not increase the cost of the summary or the size of the summary. So what's the algorithm that this enables? We make use of what are called annotations. We start by assigning annotations to the leaves of the lattice and propagate them up. Okay, intuitively, that's the big picture. An annotation consists of three components. There is a weight, which for the leaves of the lattice or the data warehouse cells are exactly the value that is present in the cell. Dimension for an internal lattice node, it talks about the dimension along which all the drill down children of that node in question are covered by the summary. Whatever summary we are constructing using this annotation based encoding, which are the children along this dimension that are covered. So that's the information that is encoded by having the drill down dimension here. Okay, C is the cost, that is the size of the resulting summary. And we propagate these annotations bottom up, and we do so by greedily propagating the most popular weights among a set of siblings along a particular dimension. Okay? As a result, of course, a node may end up acquiring a bunch of annotations. So this is step one, or stage one. In stage two, from the root downward, we repeatedly choose, again, in some kind of greedy fashion, for every lattice node, the dimension child such that along that dimension, along that drill down dimension, the cost is the least from what we can tell from the various annotations of the child nodes. Okay, so, and whenever there is a tie, it doesn't matter, we can break it arbitrarily. So here is that example again. Now, obviously, there is no way I can walk you through the algorithm for this entire detailed example. Let me cut it in half, essentially. So for a subgrid, for a subset of the data warehouse, if you will, respecting dimension hierarchies, obviously, let's see how the algorithm works. So these bunch of annotations, they correspond to the leaves of the lattice. For example, sleeping bags Manhattan, sleeping bags Manhattan. There is no magic to it. 1.1 is the value. There is no dimension node to speak of because I'm at a leaf. There is no dimension node below me. And the value here, sleeping bags Manhattan, that's a typo. That should be 1.1. Okay. And for tents Manhattan, it's 1.1. That is correct. Oh, I'm sorry, I made a mistake. So the last one really corresponds to the size of the summary. Trivially, the size of the summary here is 1.1. 1.1 is the value that I'm directly using. Trivially, the size is 1. Okay, so this is not the most interesting case. Let's move to the propagation case. First, I'm going to show you an example where propagation is not doing much. It's not really saving cost. And for that, I'm going to choose these two nodes and talk about what its parent corresponding to New York City and sleeping bags, what kind of annotation it might get. There are two possibilities. I can either propagate 1.1 up, or I can propagate 0.8 up. No matter what I do, the resulting cost will be 2. Notice that in both cases, the dimension along which the propagation is happening is the store location dimension, okay? Because that's the only dimension along which we can roll up in this case. All right, let's take a less boring example. Consider these two cells, sleeping bags Manhattan, tents Manhattan. Okay, so they both have the exact same value for the ratio of sales between 2 successive months. So what we can do is propagate that value 1.1 to the parent. So the roll-up dimension in this case is product. So we just summarize these two values with one value assigned to the parent, the lattice parent, and no weight at all for the two children. So that's how we shrink the summary from 2, which it would have been initially, to 1. Okay, this is the basic idea. So all that happens after this is you just repeat these steps. I mean, in fact, the algorithm is incredibly simple. Okay. So it turns out that fast forward, for the subgrid that I've shown, subdata warehouse that I've shown, the optimal summary has a size 3. Just trust me. I'm going to have to tell you quickly about experiments. So we conducted a detailed set of experiments on various data sets, 3 real data sets, one of which I'm not showing, and 2 synthetic data sets. You can look at the paper for characteristics of the data sets. Quickly about baselines, recall that the 2 key baselines are based on the 2 pieces of related work that I highlighted in the beginning. Karloff et al.'s algorithm, which I denote as K. Recall that it only runs on 2 dimensions, and it's a randomized 2 approximation algorithm. And it does not consider lossy summaries, okay, and does not consider more than 2 dimensions either. The other baseline is cascading analyst's algorithm due to Roll et al. A couple of sigmoids ago. It has a bounded size, but unfortunately, it does not come with any worst case error guarantee. There are other Strawman baselines that we created by, for example, stacking the dimension hierarchies in some arbitrary order, choosing random embedded trees. There are a couple of these Strawman algorithms, and TS refers to our tree summary algorithm. In experiments, we measure, of course, the size of the summary generated, the reconstruction error, which I will define formally in a second, the reconstruction error related to inferring the cell value using the summary, the running time for finding the optimal summary or finding whatever approximate summary that the particular approach promises. So reconstruction error, we make use of the so-called symmetric mean absolute percentage. So it takes the absolute difference between the original and estimated value, in this case for the cells, and divides that by the sum of absolute values of the 2 measure values, the original and the predicted or inferred. So this is bounded as well as easily interpretable. It has been used in prior literature, which is one of the reasons for favoring this. It has been used extensively in prior work. So in our first set of experiments, we compare with the Karloff et al.'s algorithm. So very quickly, we do find that Karloff's algorithm is faster. Okay, so it's faster. However, it produces less concise summaries. So let's recall that Karloff's algorithm for 2 dimensions, it's a randomized approximation algorithm, because even for 2 dimensions, their approach is NP-hard. Finding optimal summary under their approach is NP-hard. Okay. The second set of experiments we compare with the cascading analyst's algorithm. So the main highlight of this comparison is that we wanted to compare both error performance and running time performance. With respect to running time, the cascading analysts is significantly slower. And with respect to error, the average error of both approaches more or less match each other. However, the worst case error of cascading analysts is much worse than ours. Okay, and it's not surprising given that we are able to provide a bound on the worst case error, whereas cascading analysts does not have such a guarantee. And the last set of experiments, they essentially show that our algorithm scales reasonably well with number of dimensions as well as number of leaves, or equivalently number of cells of the data warehouse. To quickly conclude, in this work, we talked about summarizing multidimensional data by leveraging the dimension hierarchies that naturally come with multidimensional data sets. The main advantage of the approach we propose is that our summary is computable in polytime, in fact, quite efficiently, and it scales well with number of dimensions, unlike related work. Our summaries are significantly more concise or faster in running time, or have much better worst case error performance compared to related work. What I mean by that, in some cases, of course, our algorithm is less efficient than, for example, Karloff's algorithm. But if you consider all related work, we certainly dominate them in at least one of these 3 dimensions, in some cases more than 1 dimension. In future work, it would be interesting to consider summaries that can deal with multiple measures at the same time. For example, number of infected cases, number of recovered, and number of deaths. Sorry for that example, that came to mind naturally. What about outliers? Can we build summaries that are robust to outliers? Can we propose other means of approximations? So these are some of the questions that we're looking at. Thank you very much. I'll be happy to take questions.